So here we're looking at the Vesper Modeling Lab, in case you weren't able to be here in class or you're looking at this again and trying to complete some homework. So the whole idea, we're giving a formula. Oh, can't see that yet. All right, you're given a formula. You need to provide a Lewis structure. You need to give the shape and need to predict the polarity. All right, so I'm going to give you some cutoffs there, and let's get started. So the very first thing that we're going to use is CCl4. Okay, so this is relatively straightforward. You know carbon is going to be in the middle. It's got 4 valence electrons, so here's carbon. 4 valence electrons, 4 of them are unpaired, which means that it's going to make the most bonds out of anything. Chlorine has 7 valence electrons, which means that only one of them here is unpaired. It can only make 1 bond. And there are 4 chlorines, so we scatter them all around the carbon. Okay, and 7. There we go. Now, the whole point of doing this is that atoms want to share electrons, so they end up with 8. Okay, end up with 8 valence electrons. The only way to share is by taking an unpaired and grouping them together. So let's group them together. Okay, now, so what we've done is provided our unpaired electrons with a partner. Okay, they all have new partners. But what we do need to do is draw a legit Lewis structure, because that just ain't going to cut it. So what we're going to do is take any place where we've drawn a circle and replace it with a line. Those lines represent bonds, and each bond contains the 2 electrons that were donated into it, represented by the circle here. So this here would be your shape. Okay? Would be your Lewis structure. Now, the shape is determined by how many bonds. I see 4 bonds around the central atom, and I see 0 lone pairs. So this is a lone pair, but it's not on the central atom, so we don't worry about it. Our formula sheet, or our shape sheet, gives us that 4 bonds, no lone pairs, will give us a tetrahedral molecule. Now, for polarity, our sheet also says that a tetrahedral molecule is going to depend on its symmetry. So what we're going to do is actually build a model. Black is carbon. Each one of these little things is a bond. Carbon has 4 bonds. So let's put all these things in. 4 bonds out to 4 individual chlorines, chlorine being green. So hopefully you guys can see the colors all right. And there you have carbon tetrachloride. No matter which way you slice it, always looks the same. We can pick it up, spin it around, you look at it like that, you can cut it any way, the thing is symmetrical. Alright, you can look at it like this, alright, it's symmetrical. No matter which way you cut this thing, it is always going to look the same. So, tetrahedral molecules, when they are all identical bonds to the outside, they are non-polar. Symmetric means non-polar. Okay, symmetric means non-polar. Think about it like this. If the thing is polar, it means it's like a magnet and has poles. So things are different around it. Alright? So this thing being non-polar means that one side is just like any other side. So let's go ahead and take a look at our second compound. And this is actually a little tricky one. So we're gonna, and just remember we're going formula, Lewis structure, shape, and polarity. The formula is H2CO. So we again know the carbon's going to go in the middle. Let's put our oxygen over here. 1, 2, 3, 4, 5, 6. Let's put the hydrogen and the hydrogen. Okay, let's go ahead and connect all of our unpaired electrons. Here's an unpaired electron. Here's unpaired electrons. Well, here's a question. Do I grab that there? Yes, we think we do. And here, there's a second way to connect down to that oxygen. Okay, well, what does that mean? That means that when we go to write our true Lewis structure, we've got a carbon and a double bond down to oxygen with two electrons, or two pairs of electrons still there, an H and an H. Now, each one of these things, single bond, double bond, two single bonds, one double bond, still 0 lone pairs. Our shape reference tells us that this is going to be a trigonal planar molecule. All right, trigonal planar molecule. Now we can eyeball this and say that, hey, this side of the molecule is not the same as this side. So we can just call right out that it is going to be polar. Let's go ahead and build a model and check. Okay, so I went ahead and built a model here, and let's pull it out here. So this, you've got your carbon right in the middle. You've got your oxygen. It's oriented the same way. Now you'll notice we've got a double bond here. We use the springs as a double bond. We have to show that each one of those unpaired electrons got connected to this oxygen. Here are your two hydrogens. Okay, so all in all, we can see that, hey, if we cut this thing down like that, left and right are the same. Cut it like that, top and bottom, not the same at all. So this is not a symmetric molecule. It's got poles like a magnet. Okay, so let's go ahead and take a look at our next couple sets of molecules. We'll pull that off and label this the same way. We've got the formula. We've got the Lewis structure. We've got the shape and the polarity. Okay, so we'll go ahead and get started here. Okay, so our next one we're looking at is pH3. This would be phosphorus trihydride. Well, we look at our periodic table, we figure out that phosphorus has 5 valence electrons, which means that 3 of them are unpaired. Hydrogen has only got 1, convenient. Each hydrogen wants to make 1 bond. Phosphorus wants to make 3, so it works out quite nicely. On our second time through, we replace each one of those circles with a bond. So we see here, ooh, that shrunk down a little bit. Let me jack up the camera again. There we go. Hopefully that'll hold. Okay, there we go. So we replace each one of those circles with a bond, and we end up with a 3 bonds. Okay, 3 bonds. 1 lone pair. Okay, 3 bonds and 1 lone pair. There's your lone pair right there. Okay, so that tells us that we are a trigonal pyramidal, or trigonopyramidal, however you'd like to pronounce it. So polarity is pretty simple. Here's your model. You can see that it's pretty symmetric looking that way. Not if you turn it that way. As a general rule, anything with a lone pair will be polar. Anything with a lone pair will be polar. All right, just without a doubt, it's going to be that way. Okay, so let's go ahead and move on to the next one. This is SiO2. Move this up here. So, SiO2. Silicon's much like carbon. It's got 4 valence electrons, so it means that all 4 of them are unpaired. Oxygen has got 6. Oxygen has got 6. So, let's go ahead and pair them up. We can pair that one and that one. 2 connections there. We can pair that one and that one. Again, 2 connections. So let's go ahead and draw this out in a nice clean Lewis structure. We see Si double bonded to O. We see Si double bonded to O on that side. Now, you need to make sure that you cover all of your unpaired electrons. If you ever leave an unpaired electron without a bond, something's gone wrong. So, let's analyze. We've got 2 double bonds and no lone pairs. That tells us that this is a linear molecule, a 3-atom linear molecule, if we're curious. We'll pull out the molecule here, and we see right here. Now, to an artist's eye, or to a regular trained eye where we're looking at symmetry, this thing doesn't look exactly like this thing. All right, but we see that they're both double bonds, and actually if we get it at the right angle here, it does look pretty similar. All right, chemists aren't really worried about the actual model, what it looks like. They're worried about what atoms are on either side. We see a double bond to an oxygen on either side, and that's not going to change no matter which way we spin this thing around. If we put it up like this, we can cut a line right down the axis of the bond. We have half of a molecule there, half of a molecule there, left and right. They look pretty much the same. This overall is a symmetric, which means non-polar. Okay. Next one. Give it a bit more room. Come on up here. Next molecule we'll look at is OF2. Now, this is an interesting one. Oxygen has 6 valence electrons, yes. Fluorine has 7. Fluorine over here also has 7. So we can pair those up. Right, we can pair those up, and let's see. As we draw this, it makes it look like this thing is a straight line. But if we look at our shape guide, we'll see that that is not a case. We have 2 bonds and 2 lone pairs. 2 bonds, 2 lone pairs mean that this thing must be bent, which means a better way to draw this thing over on this side would be OF2. Be a better way to draw that. Bent. The other famous bent molecule would be water. So this one here, we can obviously see that it's symmetric this way, but not this way. All right. So anything with a lone pair on the central atom is automatically going to be polar. Okay. Let's move on to the next compound. This next compound is HCl, and this one's actually really straightforward. HCl. Excuse me. HCl. Well, hydrogen only has 1 electron. Chlorine has 7 valence electrons. There's only one way for them to pair, so it ends up with a bond right there. Oh, forgot to switch colors, sorry. Now, only 2 atoms. The only way you can do this is a linear shape. And if you take a look at this linear shape right here, you've got chlorine and hydrogen. Those are obviously not the same. So this thing is a polar molecule. Let's move on to our next one. So our next element, our next compound, excuse me, is HCN. Now, we're just going to assume again that carbon goes in the middle, 4 electrons, and otherwise it's just going to follow. I'm sorry, let me get that back in here for you. Otherwise, we're just going to follow the order that is written. Okay, we can find a single bond there. We can find another bond there. Ooh, wait, we still have 2 pairs of unpaired electrons. So let's grab that one and grab that one. So we've actually got 3 different connections, 3 different bonds going on between this carbon and this nitrogen. The electrons rearrange so that they all end up inside between those 2 atoms, and then there's the hydrogen. So here's the deal, is we've got a 1 single and 1 triple bond. Again, our sheet, our shape reference tells us this will be a linear molecule. As far as polarity goes, well, here's your molecule. It's not quite linear, but let's see if we can get that here for you. All right. All we need to do is look at symmetry. Looks okay splitting it like this, left and right. Doesn't look the same going this way. Hydrogen, not the same as nitrogen. So this one is going to be a polar molecule. Okay, on to the next one. SCl2. Here's another interesting one. Sulfur has 6 valence electrons. Chlorine, 7. Actually very similar to one of the ones that we saw earlier. We can bond there, we can bond there. So let's grab our other color pen and make that a little bit cleaner. So we have sulfur, make a bond to chlorine, make a bond to chlorine. Now again, we've got an issue where we have two bonds, two lone pairs. So this is going to end up being bent. And we know that all bent molecules, remember our friend here, so we're using this for sulfur now, and those are two chlorines. All right, all bent molecules will be polar, no matter what. Okay, let's look at our next set. Next one is actually where we start using some, ooh, wait, did I get lost? I did get lost. The next one, we skipped one, is Ni3. Now, nitrogen has 5 valence electrons and it makes 3 bonds. Iodine has 7 valence electrons, so it can only make 1. So the iodine is going to get distributed around the nitrogen. There's a bond, there's a bond, there's a bond. Pull out our other marker here, make each one of those into nice clean bonds, and make sure to put in all of those non-bonding lone pairs on the iodines. Around the central atom here, so we can all count it up, we've got 3 single bonds and 1 lone pair, which tells us that this is trigonal pyramidal. And we know that all trigonal pyramidals, even though it might look symmetric like this, you flip it up on the end, not anymore. So this one is going to be polar, and it's because of that lone pair. Okay, so we're going to go ahead and look at our first of the complicated ones here, where we've got a lot of different elements going on. So, the formula CH2Br-Cl. Now, there's a lot going on here, but let's think about it. We've still only got 1 carbon, 2 hydrogens, 1 bromine, 1 chlorine. Carbon wants to make 4 bonds, and there are 4 other things to bond with it. So, let's go ahead and scatter everything around. That was kind of sloppy, but let's go ahead and look at the others. We got H, and we've got an H. So, here's an unpaired electron, there's an unpaired electron, there's another one, there's another one. Well, it's all pretty straightforward. It works out well. Let's go ahead and draw our new clean Lewis structure. We've got 1 bond up to the bromine. We've got a bond over to the chlorine. We've got a bond over to the hydrogen, and a bond over to this hydrogen. Around here we see 4 bonds, and I don't see any lone pairs around this central atom, so we know that this is going to be, waiting for it, what do you think? If you guessed tetrahedral, you've earned yourself a cookie. So, the thing's tetrahedral, but let's take a look at it. Color's a little hard to see. Let's flip this up. Now, remember the rule we talked about for tetrahedral is that it's only going to be nonpolar if all of the atoms are the same. So, if we cut it this way, not the same. Cut it this way, not the same. Cut it this way, still not the same. So, we're going to have to conclude that this is a polar molecule. Now, all the rest of them here have got particularly interesting structures. So let's break it down, look at each one in turn. First one, C2H4. Now, we know that carbon wants to be in the middle, but what happens when there's 2 carbons? So what's going to happen is that they're going to want to go next to each other. So there we got the carbons, and the hydrogens we're just going to distribute evenly, which means that we're going to put a hydrogen around each carbon. And it's just a matter of pairing up our unpaired electrons again. So here's 1. We can do that. We can do that one, that one, that one, and that one. So this looks a little bit weird, which is why we're going to clean it up here. Each carbon is bonded twice to each other. It's got a single bond out to each hydrogen. It's going to end up looking like this. This is a molecule called ethene, or ethylene. Okay. Now the shape, it's actually going to be 2 different shapes because we have 2 central atoms. Excuse me, sorry about that. Let's go ahead and look at our first carbon. we have 2 single bonds, 1 double bond around that central atom. So we block this out, this first central atom, 2 single, 1 double. Which means that overall, the shape is trigonal planar. Around the second central atom, we again have 2 single and 1 double, which means that this is going to be trigonal planar as well. Polarity, well, this molecule is overall pretty symmetric. No matter which way we slice it, that way, cut it like that, it all looks the same. So this is going to be a, writing symmetry, all right, so it is non-polar. Take a look at the next one. It is also a compound with a lot of carbons in it. So let's give ourselves some room. This one is CH3COOH. One trick you can use to help you out is that anytime you see a bunch of carbons, break the structure down. CH3 and then COOH would be different units. So this is telling us that we've got a carbon with 3 hydrogens around it. Okay, you've got all your valence electrons there. Then you've got a carbon with some oxygens. And I don't know where that hydrogen is going to go yet, so, but we're going to take care of it last. Okay, so let's start pairing up. First thing, we want to pair our carbons. We know that this carbon is going to take care of the 3 hydrogens. All right, so again, when there's multiple carbons, these things kind of give us a clue to how the thing is going to be built. Now over here, I've got this carbon, and everything's going to try to bond to the carbon if it can. Here's an unpaired electron. Here's another unpaired electron. Now we've got a choice. We can bond this hydrogen to this oxygen or to this one. It's closer over here, looks all right that. We've still got an unpaired electron here and here. So let's go ahead and do that up. All right, now this thing is really messy, so let's clean it up real good. We've got a carbon bonded to a carbon, single bond right there. This carbon is bonded to 3 different hydrogens. This carbon has 2 bonds to this oxygen. And that oxygen still has a pair of electrons on it. Carbon is single bonded to an oxygen over here. Still has those, which is bonded to a hydrogen there. Okay. So again, we have our first carbon, our second carbon, and we've got an oxygen right there, each acting as central atoms. With the first one, we've got, block everything else out, we've got 4 bonds. So that carbon, tetrahedral. The second carbon, it's got 2 single bonds and 1 double bond, which means it's trigonal planar. This oxygen has 2 bonds and 2 lone pairs, which means it is bent. Overall, I think we can tell that this molecule is not symmetric in really any way we cut it. So this will be a polar molecule. Okay, so our last 2 are also complicated carbon-containing compounds. All right, we're going to do a special segment on these as we get further into our unit. They are called organic, all right, because they got all these carbons. We'll get into why that is. So the next one, CH3, CH2, OH. Again, the formula gives us a little bit of clue as to the structure. So we're going to set this up with carbon having 3 hydrogens around it. We've got a carbon with 2 hydrogens around it. And then we've got an O and an H. Okay, so now all we need to do is pair these up, make a bond, make a bond, make a bond, make a bond there, make a bond there, make a bond there. Here's a bond, and there is another bond. So all we need to do, clean this up now. Pretty straightforward. We've got a carbon, hydrogen, hydrogen, hydrogen. Here's a single bond over to this carbon with another 2 hydrogens on it. Here's an oxygen, and down to a hydrogen. Now, you'll notice it doesn't really matter which way we put this, as long as we make sure that the oxygen is connected to the hydrogen in some way. We've also got 3 centers on this one, 1, 2, and 3. The first carbon is bonded to 4 single bonds, so it's going to be tetrahedral. The second is also bonded to 4 single bonds, so it is also tetrahedral. The third, the oxygen, has 2 single bonds and 2 lone pairs, so it will be bent. And if we pull this out, this is what the thing looks like. It's rather large. Pull it over here. Here's your carbons, your oxygen, all single bonds. We can see that this is not symmetric, so it's going to be polar. Last molecule here, last molecule. CH3CHO. Once again, use these as a clue to the structure. Let me slide this over so we can actually see some of our polarity. Use the clue. 3 H's, carbon, and here's the other carbon. Now I don't know the order in where these things are going to go, so I'm just going to put the H's and the O's all scattered around here, because I don't know where they're going to end up. Let's go ahead and drag these here, connect that, we can put the H there. Then I have 2 more on a carbon, 2 more on oxygen. Then I need to pair. Pair those, and pair those. Works out very well. Carbon, 3 bonds, each to a hydrogen, single bond to a carbon, bond to a hydrogen, double bond to an oxygen that still has 2 lone pairs on it. This one again has 2 centers, 1, 2. The first center, 4 bonds, which means it's tetrahedral. The second, 2 bonds, 2 single bonds, 1 double, which means it's going to be trigonal planar. And if we don't believe us, let's go ahead and pull this out. We see the tetrahedral center here. All right, so all in all, looks like that same tetrahedron shape. And over here, we have that same triangle, the trigonal planar shape. Flip it up, and that side looks straight up and down. I can also see that this is definitely going to be a polar molecule, because it's not the same on either side. Okay, so I know this is a bit long video. Thank you for bearing with us. Hope this helped, and we will see you back in class next time.